You can't ever be sure of anything. Back in Europe, a guy even worked it out with numbers. That's a quote from a movie. And in the quote, they were referring to the famous Heisenberg uncertainty principle, but they got it totally wrong. Heisenberg did not destroy all knowledge. Yeah, this thing is pretty weird, but it's not earth-shattering, except maybe it is. But what is it? The uncertainty principle tells you that you cannot have simultaneous and exact values for a particle's position and momentum. The uncertainty in the position measurement times the uncertainty in the momentum measurement must be greater than h bar over 2. H bar again is Planck's constant divided by 2 pi. It's wicked small. 10 to the negative 34th power small. So don't try to use Heisenberg to win acquittal from a jury. That's what the movie quote was about. But for quantum mechanics, this is a really big deal. And here's a way to think of it. According to de Broglie, particles are waves, and their wavelengths are connected to their momentum. Not all waves, however, look the same. See that wave on the left? It gives good position data, but not good wavelength/momentum data. The opposite case is shown on the right. But Heisenberg's contribution goes far beyond that. He produced an entirely new way of looking at particles and measurements with matrices. Consider an infinite matrix, which is in a way impossible, just like it's impossible to think of something that's 10 to the negative 34th power small. But anyway, we could use this matrix to describe everything you'd want to know about a particle, its mass, its position, its velocity, its momentum, its charge, its energy, etc. But how would you find those values? With another matrix, a measurement matrix. But matrices are weird. First of all, they are not commutative. That means order matters. Do you remember how to multiply matrices? You go across the top row and down the first column and then the other rows and columns. And like we said, order matters. This is weird. We all remember that 6 times 3 is equal to 3 times 6, but that's for scalars. Order does not matter. Order does matter for vector cross products and for matrix multiplication. So, if order matters, let's define a new operation, the commutator. If A and B commute, then the commutator of A, comma B is 0. Got it? Okay, matrices. Why are we talking about matrices again? Oh yeah, measurement. We want to measure amplitude. A for amplitude, the amplitude of a particle. We multiply the operator matrix onto X and it kicks out a value. Call that value an eigenvalue. Call X the eigenfunction. Look those things up. Or consider this example. If you go through the steps of matrix multiplication, this example works out just like we promised. The operator matrix operates on or multiplies the eigenvector and kicks out an eigenvalue. The only issue here is that the eigenfunction is completely the same before and after the operation. For a physical object, this would not be the case. More on that later. First, notice that this form of measurement is very different than in classical physics. It's not passive. I heard the uncertainty principle described this way once. If you are going to try to find the location of an electron, you need to bounce a photon off of it, and that will disturb it and change its momentum. Well, that's true, but it's totally incomplete. Theoretically, you could do a conservation of momentum problem with that photon and that electron and then find precise, exact position and velocity information, but again, that's classical physics. This is quantum mechanics, and speaking of being disturbed, let's get precise about uncertainty. Here is the definition of variance. Notice the pointed brackets, that means average. Look at the diagram. The standard deviation is defined as the square root of the average of the variances. And I'm reading off the slides now because I flunked statistics, but this guy didn't. He combined the previous definition of standard deviation with the definition of a commutator and wrote this equation. Don't be scandalized by the I term yet. This one is being squared, and we are getting close. Just remember that using the momentum P operator and then using the position X operator on the matrix will give you a different result than doing those two operations in a different order. They do not commute. This is what we said earlier. You said that you can't take the values simultaneously. In other words, order matters. Good. But what is our momentum operator? Have you seen one lying around? Whatever it is, we'll need one that satisfies this, the Schrödinger equation. The de Broglie wavelength showed us that particles have wave properties. This equation describes those waves in detail. The wave function, psi, can be thought of as Schrodinger's take on the Heisenberg infinite matrix, but I don't want to make it sound like these two physicists were using the same approach, because they weren't. Anyway, psi doesn't tell us the particle's properties exactly. It tells us what they might be. Here's an example. If you've heard of interfering waves, you're familiar with the diffraction pattern on the right, but you might not know that that same pattern can be made by electrons. Again, thank you to de Broglie for helping us find the electron wavelengths. But it gets even weirder. That diffraction pattern, again, it is not just two piles of electrons, one behind each slit, but a diffraction pattern. It's made of individual dots, individual electrons hitting the screen. But here's the question. Which slit did an individual electron go through? Answer? Both. It went through both slits and then it interfered with itself. That's what psi is, a wave function that gives probabilities of being here or being there, but it doesn't stay that way. The electron, after it hits the screen, it makes a dot. It is measured. The operator, the screen location operator, acts on the wave function and kicks out a measurement of position, a dot. No longer is that wave function just a collection of probabilities. It has been collapsed, and it's giving you a location measurement. And I know what you're thinking. The electron can't really go through both slits. You're just saying you don't know where it went. I know what I'll do. I'll just put a little counter by the slits and count how many electrons pass by. Well, you can do that, and you will count electrons, but when you do that, you are, quote, seeing the electron at a location. You are spying on the wave function. You are collapsing the wave function. You are operating on that wave function and changing it. So you're having an effect. You're not being a passive observer like you can be in classical physics. The probability wave, again, satisfies Schrodinger's equation, which is complex. Wait a minute. dt and dx in the same equation, is that legal? Yes. And it's even expected from the classical wave equation. Anyway, we're not solving these equations. We're just using Schrodinger to find this, our momentum operator. Excuse me, at this point I need to interrupt you and tell you that instead of explaining anything, you're just adding confusion onto confusion. Guilty. But how could I ever understand that? You can't. But you can get used to it. Anyway, this is the momentum operator, and we are almost done. And this momentum operator almost makes sense if you consider that k equals p squared over 2m. Anyways, wait a minute, is this thing just a conservation of energy equation? No, it's much more. But anyway, we have the operators, and they don't commute. Gross. Give up. I'm turning it off. I hate this. This is ridiculous. No, wait a minute, listen. Stay with me. Take a deep breath. This isn't too bad. You don't need that much. It's ugly, but you don't need really too much calculus to follow these steps. It's just the product rule. Two of the terms cancel out. They're well behaved. It's okay. Anyway, let's now put these operators into that Robertson equation. Very good. And remember the value of their commutator. Very good. And we're done, which is pretty exciting. Maybe not that exciting, but definitely different from classical physics. You can't have simultaneous, order doesn't matter, exact values for position and momentum. And this relationship works for other quantities too, like time and energy. Don't worry, I'm not going back to the Schrodinger equation at this point, but check this out. From classical physics, impulse equals change in momentum, force times time. Work is equal to change in energy, force times displacement. Rearrange, cancel out, and there you go. Notice, force doesn't stay in this equation. Force is going away now. It's kind of lost in the shuffle in quantum mechanics, which is kind of sad. But anyway, you cannot know the exact energy at an exact time. You can only know average energies over time intervals. But this doesn't mean we can't know anything. And if you have listened this far, please excuse me if I end on a tangent. I have heard it suggested, even by science professors who should know better, that Heisenberg has something to do with the debate of determinism versus free will. Heisenberg does not have anything to do with that debate at all. The line of bad reasoning goes like this. Classical physics allows us to know the future of any particle based on its current state and the forces acting on it. Any particle, even those particles in your brain, the ones that move around when you make a decision that you think is free, but after all, it has to be determined by the laws of classical physics, right? Wrong. Anyway, the bad reasoning continues and says, after Heisenberg, there's some uncertainty, there's some quantum foam, there's some uncertainty, and now Great news, we can have free will again, because at the crucial moment there's wiggle room tucked away 34 decimal places after the zero. And like I said, that's terrible, faulty, horrible reasoning. Why is it bad? Because particles don't make decisions. Particles don't have free will. Humans do.